Hello, everyone. So we're going to shift gears. You've probably seen this before. So my name is Rémi Duquette. I'm the Vice President of Industrial AI at Maya. Industrial AI means taking engineering knowledge all the way to operations, manufacturing, and then later on even usage or operations of the designs. The focus we have at Maya is really to empower people. In my group, we empower people through the use of new machine learning, deep learning, and artificial intelligence. My colleague René showed some of the more leading edge ChatGPT large language models. I will go a little bit on the industrial side of that, so more on the deep learning side and machine learning side. So you can get some examples, some tangible examples of what we've done in that industrial environment. So first, I mean, you probably have gone and seen these before, right? In terms of data, most people in the manufacturing industrial sector still use a lot of spreadsheets, right? A lot, way too many. And often it goes unmanaged, right? So my colleague from the PLM team probably showed you how you can then slowly move into a more digital world. As you move to a more digital infrastructure, you're going to collect more and more data. Initially, yes, design data, engineering data, and eventually manufacturing data, and then at the end, operational data from those designs. So you can get some full circle feedback and collect a lot of information that you didn't have access to before. So there's a lot of data that's required to make a good machine learning, deep learning model. I'll talk to that, but not just quantity. We're not talking about just the large language model equivalent and gigabyte of data. We're talking about variance in the data and quality in the data. So I'll get to that later, but a lot of people somehow mistakenly take data for machine learning as we need a lot of data. That's not necessarily true. What you do need is a lot of variance in your data, because machine learning will learn a lot faster using variance. And I emphasize variance because often when we go in manufacturing, people have been optimizing their processes over years, right? Small, tangible improvements, but incremental improvement. What that does over time is it erases the variance, because now you're just fine-tuning the process to make it 1% better, right? Which is great. And then you make another small change, another 1% better, which is great. But if you give that data to a machine learning algorithm today for the last 3 months, the variance will be related to episodic things, but not truly the core of what you're trying to accomplish, which is, change the process itself. But to do that, you actually need variance, real variance in the data that you have. So anyway, lots to talk about on the data side. Lack of standards on the methods and the process, that typically is still valid, and we'll get to that. Poor integrations with third-party systems. Here we talk about data systems, right? So you may or may not have access to all the data you need. So Maya, we help you harness that data and synchronize that data into standard infrastructure. We're going to talk about Insights Hub and some industrial data gathering that you can push your data to and standardize your templates in there for the assets. Subject matter experts. In terms of AI, we tend to forget that typically there's still human in the loop. Whether you talk about manufacturing today, of course, manufacturing plants are becoming more and more automated with more and more robotics in them, fine. But at the end of the day, it's not true that it's 100%, you push a button and it produces something and is being shipped and received by the client. There's a lot that goes into the whole process. So human in the loop is important, and augmenting that human in the loop is very key at this stage, because a lot of the small manufacturing processes have been optimized. So a lot of other kind of key challenges. In the end, the benefits are huge of investing a little bit in machine learning, deep learning, and AI in general. You have really 3 ROI map elements, right? You have the cost reduction. Those are the easy, low-hanging fruit typically. But the biggest item are typically the revenue generator, so the aftermarket services that you're going to be able to build based on the new knowledge you have and insights you have on your own products, right? Think about predictive maintenance on the field. If you sell a product and you sell it as on the hour used, right, all of a sudden you have a new business model. And if you fine-tune your own maintenance on your own product, well, you can generate a lot more revenue. So the upside on the revenue typically trumps the smaller cost components. The other aspect is the risk mitigation. When we talk about predictive maintenance on the shop floor, well, that can be huge. I just came from earlier this morning, some clients of ours were on the forecasting side. Before we put the forecasting models in, they had some electrical trips. So breakers were essentially just snapping out. And what happened is it actually took down an entire line for 30, 45 minutes. And that cost was huge, right? It didn't happen often. So in terms of data to feed an AI model, difficult, right? So my friend that just went before me on the simulation side, another big value of simulation is the fact that you can typically simulate very well the onset of failure. Not necessarily the failure itself. That typically can be a little bit trickier from a pure simulation perspective. But the onset of getting to a failure mode typically can be simulated. And that data can become relatively big data, right? You run a bunch of simulations close enough to a failure mode, you collect that data, and you match it with your real-time data, and now you have the normal operations, typically is what you run with. If you have issues day in, day out, there's probably other challenges that you're having, and you're probably out of business anyway. So today, it's really, most of the data is normal operations data, and the rest of the data can be simulated with simulation models. Now, it doesn't happen overnight. Every time I meet new clients, we tell them it's a journey, right? And we remind them to start from their current business challenges. Don't think right away at the magic wand of how you're going to apply AI and it's going to save, predict all your problems ahead of time and solve and forecast all the things that you want them to forecast. That's the pitfall. So you need to go back to the square one, which is what are your tangible problems today, right? Let's look at your data. Let's look at your processes. And let's look at where we can apply AI and machine learning to help you get to a better place. And then once you have that roadmap, then it's easy. The benefits will come, right? You'll have early benefits that will come, and then you'll get to not necessarily a magic wand, because I don't believe in those, but I do believe in major impact in your operations. And you can get there if you take those steps. So why Maya? Maya, you've probably known us on the engineering side for 40 years. My group at Maya has been close to a little bit more than a decade, 12 years that we've created that group, which really focuses on extending through data-driven approaches the engineering knowledge into manufacturing and into industrial operations. So we've delivered so far about 150 plus projects, machine learning data, advanced data projects, all in, or except for one, all but one in industrial operations and manufacturing. And it's collecting overall those 150 client projects, more than 5 million telemetry points, real-time telemetry points, or data from a camera or data from an audio sensor or other types of telemetry. So all sorts of sensors, but yeah, that's why I think we are experts in leveraging industrial data, and I'm going to call it dirty data, because it's dirty on your shop floor whether you like it or not. things will change in ways that marketing signals do change and are very hectic and eclectic. But industrial data change in very subtle ways. Your process changed. You think it's an anomaly? No. Outlier? No, it was the golden batch of the day, right? If you're doing batch manufacturing. So there's all sorts of things that you need to learn in a manufacturing shop floor. And if you think of your raw material that comes at the beginning of your process, how does it relate, right, those properties at, let's say you started at 8 a.m. to the finished product at 10 a.m. There's lag in each of the time series, right, on all the machines all the way to the product. Well, that kind of data engineering that you need to put in and feed to a machine learning to learn the right thing is why you would like probably to have us help you in those industrial operations. So what are we delivering initially? If you are about to get started or you want help to know how to build your roadmap, we have a consulting group that will help you establish your roadmap, where you're at today, where are your gaps, right? What kind of data you have, and based on your business problems, which ones can and should be solved with machine learning and which one shouldn't, right? There are things where it's not worth applying machine learning to. And there are lots of cases on that. And then we have a whole group on the data strategy side and data engineering and data pipeline. And 60% of the work, I can promise you in advance, will be in that second bucket. Sensor fusion, sensor gap, adding sensors, collecting data, cleaning data, organizing your data in the infrastructure. That's the big one. Once you've gone through that, then you can still leverage us if you love us. Or you can use your own team to deliver great machine learning models on top of it. Because now you're going to be on a great foundation, right? Now you're going to be able to apply all sorts of amazing projects. A typical roadmap looks like this, where we're going to look on the x-axis as the business use case value. So that typically comes from you as an estimate. We work with you to tell you if you're in the right ballpark based on those 150 other projects we've done. On the y-axis, we'll tell you, right, from a Maya perspective, roughly how much work it is to deliver the value. And then based on that, you have a bunch of dots on that heat map, and we tell you where the quick wins are, right? And then you build your roadmap and tackle them one by one or in series or in parallel, depending on your staff effort and budget. This is just a project Canva. You'll have access to it with the presentation. And now I'm going to get into the digital twin because that's really where I think most of the action is. Digital twins solve a bunch of tangible problems. If you think of the inside of an oven, you can simulate it, but placing a sensor in there might be problematic. You could use thermal imaging cameras from the outside in. There's some few things that you can do, but by and large, there's a lot of physical places where adding real sensors will not work, right? So building digital twins that correlate to an inside temperature point or pressure or flow rate, right, from other sensing devices that you already have in place now makes a lot of sense. So a lot of the use case for digital twin, an executable digital twin on a specific nature, is really about that, is to find out things in real time that you cannot otherwise find out with other methods, right? So that's the big value add. Now, a lot of people say, yeah, well, I have a lot of engineering simulation models, right? Are those digital twins? Well, most of them are pretty static, right? You'll give them static conditions, and you're going to get one result. Or you're going to get a transient run if you're lucky, so a little bit more dynamic, but it's still based on these exact one transient run, right? It's not a real-time evolution of what you got now. So the big kind of value here on the digital twin that's executable is, yes, it can be physics-based, or it can be data-driven, and we'll show you the spectrum there. There's lots of methods we can apply. or it can be hybrid in between, some real-time data, some simulation data, as I've said before. But in the end, it produces a model that will take inputs, real-time inputs, and will generate outputs. It can be in real time, near real time, depending on the need, right? And the compute that you can put on the shop floor. So Siemens, they have great edge devices from the industrial sector that we can bring in and load with those digital executable twin. And will produce real-life data with outputs and augments the value of your engineering work. Now it's live on the shop floor, helping your operators or your shop floor workers do a better job with your engineering knowledge and from the modeling aspect. Digital twins come in different size, shape, and form. I've used this rabbit. I'm from the farm, by the way. I grew up on a farm, so that's why I've used rabbits. It's an easy way to explain. You have the real rabbit, and then you have different renditions, right? Different models that you can use with different fidelity and accuracy that you can build. Sometimes you want something to run real fast, and you may not care so much about the minute accuracy of your model. The coarse rabbit may run in real time alongside everything else you've got running. In other places, you may not want to run it in real time. Maybe it's every 5 minutes, every 15 minutes, but you need an update that's a lot more accurate. Well, you can build, right, those tailored digital twins that are closer to that fine modeling. In both cases, in all cases, the digital twin have 3 levels of applicability in the industrial sector. There's I'm going to call it the virtual sensor. That's the easiest, smallest digital twin equivalent, right? Think of putting a temperature sensor in the middle of an oven where you can't possibly have a physical sensor. The other aspect would be more of a physical object where you have multiple, like a pump or a conveyor belt or something else that's an asset with multiple inputs. And then you have a process which could take 600 to 10,000 real-time telemetry points and other types of inputs that you can build a digital twin for, right? In all cases, some of them can run in real time, and some of them can run in near real time or episodically as needed. So this is just the simplest example of the lightweight pump. And we always use that as an example because it's an easy example to understand. There's a lot of problems, whether it's cavitation, misalignment of the bearings. There's different things in pump that come back, right? So the failure modes are fairly well known and something that everyone can relate to because actually there are lots of pumps in your on your shop floor if you have not noticed. Maya, we've done a lot of those in different industries. On the marine side, on the pulp and paper side, on the lithium batteries for electric cars, in the A&D with robotic arms for composite. So we've touched many different applications and sector, and the process is very similar, just very different data sets, right? This discrete manufacturing will have very specific intricacies of how you collect the data. And typically, it's more of how you relate data over multiple discrete steps in the cycle. Because sometimes, right, you'll have shop floor workers put a part on the side and say, I'll get to that one later, and move something else in front. Well, all the data that is being collected in all the next steps are no longer related to the sequential aspects of how the product come at the end of the line. Because there's things that are being moved around on the line. So there are different data things that need to be thought through. But in any case, whether it's discrete manufacturing, real-time operations, continuous manufacturing on the pulp and paper or oil and gas or energy distribution, or batch manufacturing is kind of in between, you can build those models the same way and deploy them. In terms of the deployment, you can see here a simplified model where you can start with very sophisticated 3D models and physics-based models. You can simplify them using either Amesim or other reduced order models that can condense your 3D elements into a smaller footprint. And then you can export them through ONNX is a format that is often used for vendor neutral kind of deployment, or FMI, if you know that term, for deploying your different models on an edge device close to where the inputs are. So it can run in real time. So the ONNX or the FMI files or models are really the brain that you've trained to deploy your executable digital twin. As I said before, Maya, from physics-based all the way to data-driven and anything in between, we've done it pretty much all at this stage. And sometimes physics-based is the way to go, right? If you don't have enough failure data, a physics-based system to augment your data set with onset of failure modes, great use case there for physics-based. Data-driven, if you have lots of data and you have a lot of variance in your data, then typically data-driven will be a better choice to start. So again, depends on your situation and your context. Again, this is simply the way we deploy these problems. Data sources. Trying to do a time check here. We're good. Data sources. Maya is great at harnessing various types of data. So you're probably more familiar with the traditional sensors and time series type of data. Whether you deploy Insights Hub from a Siemens perspective to collect your industrial IoT type of signals or other systems, we can help you build dashboards that will make sense. And again, we're not going to plaster your walls with a bunch of dashboards that are never looked at. We typically try to put an HMI, a user interface, that will be summarizing your state and status first, right? Think green, yellow, red lights. And then you can click when there's a yellow or red light and get the drill through and access to the real information, right? You don't want to overload people that are already overloaded with various screens. You want to give them synthetic type of data to look at. We have used a lot of audio sensors lately, mostly because we've figured out that vibration sensors are quite expensive, and often to deploy, it's a little bit longer lead item. And if you've ever walked a manufacturing shop floor, you've probably heard someone say, I'm hearing something weird, I'll come back to it later. Well, that I'm hearing something weird is actually an acoustic signal. So once we started hearing that from shop floor workers, especially older folks that know and have lived in those factory shop floors before, well, we've started putting some very cheap audio sensors in there. And lo and behold, you just do a fast Fourier transform, right, in real time, and you get this spectrum of frequencies, and yeah, the spectrum is changing. If the oil is getting dirtier and dirtier, there's a subtle but real change, right? And someone that's been there for a long time will notice it. Well, the mic will also notice it. So now we can alarm that same shop floor workers to say, you were right, and this is the device, and now you're a week early, right? Before something really starts to crumble. And then later you get the vibrations. And now you're real close to failure, so maybe it's a bit late. But anyway, so those are interesting new sensors we started to use. 2D video streams, very easy to harness. We've gone a step further at Maya with 3D stereographic cameras to build the sense of the depth in either your shop floor or for robotics components that are moving around town. So to avoid collision with human beings or other people that are in that same. So from a security and safety perspective, there's a lot of use cases there that are very real that can be deployed. Thermal imaging cameras. It's not just about hotspots. It's how the heat is propagating and how it might be generating other problems or signaling other types of issues. If you look at an electrical panel inside the electrical panel and you put a little thermal camera there, you might see electrical problems way before they occur, okay? So that buildup, right, that heat signal is something that can be learned like any other screens. Machine vision has been very heavily worked on, and thermography is actually a good, thermal imaging is also a very good way to apply machine learning and deep learning in that field fairly quickly these days. My colleague René mentioned the large language models, so I'm not going to stick to that. But a lot of people I talked to lately asked me to deploy faster our local on-prem private chat software solution because they don't want at 2 a.m. to call their boss. That's actually, someone told me that this morning, so it was kind of funny. I said, what? Yeah, last weekend I called at 2 a.m. and he was pissed. Well, I would be pissed too. In any case, so that was kind of a funny use case of if you could troubleshoot using a chat equivalent, a colleague, or a bot that has learned from your own private information, but that says local because it's your secret sauce most of the time, right? The operational aspect of a process manufacturing or manufacturing operations in general it's your secret sauce that's baked into your documentation. So you're unlikely to just want to push that upstairs in the cloud. But anyway, so that's one of our use cases. A bunch of use case clients. I'll start here with the, mentioned earlier, the lithium batteries for electric cars. So how did we deploy here the digital twin? So the last bullet is the most important one, and that's one I'll focus on. So if you look at lithium batteries, how they're produced towards the end, at least in their process here, it came out of an oven. And before they could actually test the battery and package it and ship it out, they had to wait 24 hours because the lithium was settling down. And as it settles down, you don't know if you have a good battery or a bad battery, so that's why they were waiting 24 hours. Well, lo and behold, by putting the discharge curves as a function of temperature, then you see, yes, most people think as a function of time because they track as a function of time. But when you look at the temperature variations, actually the discharge variations as a function of temperature, then you would see that after a while, having a digital twin to compare against what it should be versus what it is, you very quickly find out if the delta is growing over time, you have a bad battery. If the delta changes and actually gets closer and closer to what the nominal values are supposed to be, then, or it's oscillating back and forth around that nominal, you know you have a good battery. And actually, you know it 10 hours earlier. So instead of waiting 24 hours, they were waiting 14 hours, and they were shipping the batteries, they were packaging them, shipping them 10 hours earlier, and essentially continued to cool during shipping. So that was a big, big gain for them. Completely different industry, pulp and paper. Again, I don't know how many of you bought toilet paper when COVID started? Okay, please. I can't be the only one. We all rushed out to buy toilet paper. I still don't know why, but anyway, or wet cloths that we can use. But anyway, it's besides the point. The pulp and paper industry got hit in a big way in terms of they had to increase productivity, right, with reduced staff on the shop floor, clearly. So in those cases, we had started to work with a client, and they had 600 different telemetry points over the entire food chain of their manufacturing. And in their case, there are 20 quality parameters in what they call technical paper, toilet paper or tea bag paper. And those 20 quality parameters needed a little clip of a snippet of the roll at the end of the manufacturing chain. And it took about 30 minutes before the control room got the results, and then they were pushing it back, and then so on and so forth. So they were wasting a lot of material at startup time to begin with. And then when they went out of deviation with younger folks on the shop floor that were trying different things, again, variance, Great thing for machine learning. So when we showed up, we looked at their data from the last month alone, because they had lots of young guys touching all sorts of things to try and improve the situation. We got a lot of variance. And actually, we trained models based on those 600 points because thanks to their inability to control the process at that time, which now they're thankful because they generated a lot of data. They were not so happy at the time, but no, now they're happy. So that's another example of a digital process. Reducing unplanned downtime. So conveyor motors, very few will fail, but when they do fail, it can be pretty devastating for your production and your OEE and other parameters on your production. So in this particular case, it was really to augment the mean time between repairs, right, so that there's fewer unplanned downtime, and be able to go and replace the faulty motors before they got you in trouble, right? So that was kind of the thing. So about 27–30% of them we were able to catch upfront before they failed, and that in itself augmented a lot the time between unplanned downtime. Oil and gas, and there, again, I'm giving you a bunch of different industries here, so you can see that, you know, from leveraging data and engineering, there's plenty of places where you can leverage your data for digital twins and for machine learning enabled digital twins. This one here I particularly like because of the signal it gives. Just before the line there on the left is PID controllers. PID controllers are everywhere, right? And the reason we never replace them is because they're extremely robust and they never fail, right? Or very rarely fail. They're extremely reliable. They will always catch up to your signals. That's why it's PID. It's proportional to your signal, so it always catches up. So it's never accurate. That's why you see all the, you know, back and forth swings in the signal. But again, your process will always run. Reinforcement learning on the right-hand side, right, can be now embedded as an if condition. So if you're within your normal-ish parameters, right, why don't you run a more efficient model, control model, and if you go outside of those normal parameters, default back to your PID controller. It's already there, right? So we just essentially put an if-else statement inside the PID controller loop and embedded, right, run the reinforcement learning AI agent when things are within the bounds that you think there's no risk or limited risk, right? And no matter what, if it fails, it would default back to the PID controller that will catch up and restabilize your system. So there's really no risk there. So that's one example that we've done on a hydro treater component. I presented a few weeks ago on anomaly detection with the Canadian Steamship Line. Unfortunately, they had a little strike to go through last couple of weeks, a few days, but they recovered now. They're all operating again. So these are mini floating factories. They have about 65 of them worldwide. About 20 are within the St. Lawrence Seaway, all the way between the Great Lakes and out to the St. Lawrence Gulf outside to move goods. They move dry goods, so that's why we call them mini factories, because they're self-loader and unloader, meaning under the belly they have these huge conveyor belts that essentially takes the dry good out, and then you see the boom on the top side. It can swivel around at shore. So at shore, there's no need for any machinery of any sort. It just dumps it there on the containers at shore. So it's a specific trademark that they've developed on this. When we met them about 6 years ago, it was pen and paper type of industry, right? So in terms of digital transformation, we instrumented, put black box. By the way, a lot of those, when they go out at sea, it's through SATCOM. When the crew is watching their favorite episodes of something, the bandwidth is not much. So we don't pass through all the real-time telemetry data, funnily enough, because the priority is given to the crew for mental health reasons, which I think is the right way to do it. But in any case, it limits the bandwidth for the data we can push through. And we've made sure that we put asynchronous kind of dump of the data back to a central system so they can make all their machine learning and anomaly detection work for them. So we have about 1,000 smart anomaly indicators that are running real time and feeding to the captain and to the crew to go and fix things as they happen. So it's been quite a success story on the anomaly detection side for us and for them. eBay, you might know, a small company. We did some interesting forecasting modeling for them on the cooling versus server side. So if you cool too much your data center rooms, what happens? Money flies out the window, right? If you don't cool them enough, you burn up the servers earlier, money flows out the window. So you have this very narrow field of view from an engineering standpoint where you need to just send the right amount of cooling and not too much more. And because of their growth over time, it was a lot of millions of real-time telemetry to balance out and do the forecasting for them. So an interesting use case there. This is where we first looked at, and there's a NAFEMS paper that I published at NAFEMS a few years back on how we went from 3D CFD simulation to an Amesim system level model to a real-time agent from reinforcement learning. So that full loop there is available in the paper. So next steps, right? Maya has a deep bench to help you create and focus on the right digital twin and AI modeling approaches. We have a very specific and successful recipe that we've tried out with a lot of our clients, where we start in an agile way. We look at your business case, we look at the data, and if it's the right approach, then we start and we put a minimum viable machine learning element into your real operations. Initially, it can be in probation mode where it's only there, not used, right? But it's there, so you can query it, understand how you're going to interface with it, and then eventually you move it to production area. So if you've liked what you've seen today, and if you'd like to have a private conversation on anything, just scan those, Get AI Ready or AI in Manufacturing. Those are two papers we've published and might be helpful for you. And then you can also contact with my email if you have more questions.
Excellent. Thank you, Remy. Thank you. Let's give him a round of applause. Yeah, that was fantastic information, but also felt like drinking water out of a fire hose because there's so much to learn. I'm sure some of you feel like that about most of the day. Any questions off the top of your head for Remy based on what you saw, or any clarifications or any of the use cases that he presented?
These learning agents that you talk about, they can be implemented, let's say, in existing structures of PLCs or computers?
Mm-hmm. Yeah, so the way that they're deployed depends on the local infrastructure that you have in place. They can run on, close to the SCADA system or PLC, right? That's the best way. And we typically would latch on a small edge device. I don't know if you've seen the Siemens IoT 2050 or 2040 or nano boxes, but a small edge device that can run the compute to run it separate from the infrastructure that you have in place. So it does not bother what your SCADA systems or your PLCs in place, but it connects to them for fetching the data. And then we run locally on that small footprint of an edge device there. And feedback it sometimes directly into the HMI if you have HMI already in place. Yeah.
Thank you. Any other questions?
They want to see the robots. They don't want to
We're tired of seeing you and me. All right, please give Remy another round of applause. Thank you, Remy.